Rajeshwari MJ. She pursued her BE in Electrical and Electronics at the People's Education Society College of Engineering, Mandya. She pursued her MTech in VLSI Design and Embedded Systems at the Sri Jagadguru Balagangadharanta Institute of Technology, Bangalore. Her personal skills lie in good verbal and written communication skills. Her areas of interest lie in OOPS with C++, renewable energy sources, HVDC transmission, digital relays, automotive electronics, advances in VLSI design. She has also had papers presented at the national level, such as the Innovative Architecture for SoC Multi-Core Hybrid Processor, presented at the RNSIT, Bangalore.
Welcome to UGC lecture series of BSc Applied Electronics. Today we are dealing with the subject digital electronics. Now we are going to narrow down in the digital electronics, that is analog circuits. The analog circuit is one of the part in a digital electronics subject. In analog electronics, we already covered about the operational basics and now we move on to the operational amplifier application. In analog electronics, we already dealt with op-amps basics. Now we are going to deal with the op-amp application. So, what are the applications of an op-amp? So, op-amp can be used as an amplifier. So, there are different types of operational amplifier that are non-inverting amplifier, inverting amplifier, summing amplifier, voltage follower, integrator and differentiator. These are the op-amp application. So, these all these things we are going to apply the op-amp and this will going to helpful for getting a desired output. So, very firstly we start with the non-inverting amplifier. As we already dealt in the previous session, that non-inverting amplifier is an amplifier where the non-inverting or positive terminal of an op-amp is given a supply and for the inverting terminal is grounded. So, for a closed loop, the inverting terminal will be having a negative feedback loop with feedback resistor RF and input resistor RI. The figure shows the non-inverting amplifier where we are going to find V in and VDF, V difference, that is a difference of input voltage and feedback voltage, and with the negative feedback with the RF and RI voltage. So, the derivation of the closed loop non-inverting gain we already derived, that is equal to 1 plus RF divided by RI, and also the input impedance for non-inverting amplifier, that is equal to 1 plus open loop gain into B, the attenuation factor, all multiplied by input impedance. This is the internal input impedance of an op-amp. Similarly, the output impedance of a non-inverting amplifier is equal to Z out divided by 1 plus open loop gain into B. Next we move on to inverting amplifier. The same way in the inverting amplifier, we already know the inverting terminal, for the inverting terminal the supply is given and the non-inverting terminal will be grounded here. So, for a closed loop, the inverting terminal will having a series resistor RI, input resistor, and also a feedback resistor RF. From the figure we can observe RF and RI and also V in given to the inverting input. So, this open loop closed loop gain for inverting is also derived and we know that that is equal to minus RF divided by RI, and input impedance for inverting is equal to RI and output impedance for an inverting amplifier, that is equal to Z out divided by 1 plus open loop gain into B. So, next we move to one of the important application of op-amp in summing amplifier. The summing name itself indicates that we are going to use the amplifier for summing the input values. So, whatever the inputs that we are going to give to the op-amp, that will be added and the added will be come out as an output in the output terminal. Summing amplifier is used mainly the configuration that used in a summing amplifier is inverting op amp. So, and also the averaging amplifier and the scaling amplifier are also variations of the basic summing amplifier, because the basic summing amplifier should be the base for these two, the scaling as well as averaging. Averaging we know, if it is having n number of input means that whole n number of input is divided by the sum of the total inputs. So, the total inputs divided by number of inputs is give that will going to give the averaging. So, whatever the basic summing circuit is required, that will be provided by this summing amplifier. So, using the summing amplifier we can also enhance the circuit for getting averaging and also scaling. The summing amplifier with a unity gain. So, with unity gain, how does the summing amplifier will behave? So, summing amplifier will have, here we consider the summing amplifier with two inputs, that is V in 1 and V in 2, and we can also consider 2 or more also, but here we consider V in 1 and V in 2, and its voltage is proportional to the negative of algebraic sum of two inputs, that is V out is equal to minus of V in 1 plus V in 2. This will be the output of summing amplifier. This can be derived with the help of, we can derive in the next slide. So, this is how the configuration of the summing amplifier with a unity gain will be. Here V in 1 and V in 2 are the two inputs voltage that are applied, and I1 will be the current in the R1 and I2 will be the current in the R2 and I2 will be the current in the feedback loop RF, and is flowing through RF. Next, we consider how this summing amplifier will be having a unity gain and how this current will going to affect in a summing amplifier, how we are going to able to get the negative of summation of all the inputs as an output. So, first thing that we are going to assume in a summing amplifier with unity gain is IT is equal to I1 plus I2. So, this is the first thing that we are going to consider, IT is equal to I1 plus I2. So, since we from the circuit we can able to know that V out is equal to minus of RF into IT. This is what the V out from the circuit we can able to get. So, minus RF into IF is the value for V out from the circuit, and also V out will be, now V out will be equal to minus of I1 plus I2 into RF, that is equal to I1 plus I2, that is equal to RF. This is what we are going to get from the circuit, because IT, the total current, that will be equal to I1 plus I2. This is what the feedback current also, IT is equal to, IT will be nothing but IF, feedback current. So, this IF will be substituted with the IT, that is I1 plus I2. So, that V out can be now represented by minus of I1 plus I2 into RF. So, this can be rewritten as V in 1 divided by R1 plus V in 2 divided by R2 into RF. So, we now if we consider all three resistance are equal, R is equal to R1, R2 equals R3, then what will happen? V out, for the V out equation, V out is equal to minus of V in 1 divided by R plus V in 2 divided by R, that is equal to R. Since RF we consider all, RF is also, this is RF, R1 is equal to R2 is equal to RF. So, V out now will be After simplification we will get V in 1 plus V in 2. So, this is the output voltage of a summing amplifier which is having 2 inputs. So, the output we can observe from the derivation, the output will be the negative of the sum of 2 inputs, that is V in 1 and V in 2. So, this will be inversion of output, the magnitude will be same as the input, the sum of the input will be equal to output, but having a negative because of the supply that we are going to give the input to the inverting terminal. So, for n if the number of inputs that we are going to give will be, if n inputs will be given for a summing amplifier, what will be the expression? The expression for n inputs will be V out is equal to minus of V in 1 plus V in 2 plus V in 3 till V in n. This is what we will get for an n inputs, and this will going to give the expression for a 2 input summing amplifier. Next we are going to use the expression that we already derived in the previous slide. The problem is determine the output voltage in figure. The output voltage can be easily determined with the help of formula V out is equal to minus of V in 1, V in 2 and V in 3. Substituting the values for these 3 voltages, we will get the output voltages 12 volts for the problem, and the circuit for this is shown here with the 3 inputs, summing inputs. The output will be 12 volts. Next, summing amplifier with gain greater than unity. If we discussed till now, it is for the summing amplifier which is having a unity gain. If suppose if it is having a gain more than 1, what will be going to happen? So, then when RF is larger than the input resistors, the amplifier has a gain of RF by R, where R is the value of each equal value. So, the general expression for the output is, the output voltage will be given as minus RF divided by R, that is multiplied by V in 1 plus V in 2 plus till V in n. So, for the output greater than unity, we are going to have an expression, that is V out is equal to minus RF divided by R, where R is the value of each equal resistor and the input resistor, that is R. The general expression will be like this. The output voltage has the same magnitude as the sum of all the input voltages and which is multiplied, but the gain is not unity, we need to multiply this with the help of RF divided by R, because we did not consider here like what we considered previously, the resistor value are equal. If unity gain is greater than 1, the resistor values are not equal, and we need to multiply the same expression with a constant value, that is minus RF divided by R. Next, the another versions of the summing amplifier. The summing amplifier is a basic one for averaging amplifier. So, keeping in mind with the help of summing amplifier only we are able to get this averaging amplifier. So, summing amplifier can be helpful to produce this averaging. Also, this is done by small modification, that is setting the RF by R equal to the reciprocal of the number of inputs. That is what we need to change the value of resistor, that RF and R ratio should be equal to reciprocal of the inputs, number of inputs to the circuit. That will going to be helpful for averaging of an amplifier. This is a settings that we need to remember for averaging amplifier. Next, we move on to another example. Show that the amplifier in figure produces an output whose magnitude is the mathematical average of the input voltages. So, we are going to have a circuit that with the different voltage value and as well as current and as well as resistor values. So, we need to show that the output will be having a magnitude that is of averaging of input voltages. So, now we consider that this resistors will be of different values, that is R1, R2, R3, R4 of same, but RF is different. So, we need to use the formula V out is equal to minus RF divided by R, and similarly summing all the input voltages. So, substituting for this formula all the equation, we will get finally minus 2.5 volts as a V out, that is as an output voltage. So, from the example what we learned is even the resistor value and the feedback resistor value are different. We need to use this formula and to get the output of an voltage. Output of voltage will be summing of all the input voltage divided by the number of inputs will give the V out of an summing V out of an averaging amplifier, which is having different number of different values of resistor. So, voltage subtractor is the next topic. So, till now we studied about the summing and its different variations. Now, we are going to deal with voltage subtractor. Subtractor in the sense we need to have a output that is having the input subtraction. So, we need have a difference of two input should be the output. So, if we give two inputs voltages of different values in the input, the difference of two inputs should be the value of output. That is what we need to decide in a subtractor. So, here that subtractor circuit will be like this, which is having V1 and V2 as the input voltage with R and R3 as a two resistor for the inputs, and RA will be the feedback resistor and R4 will be the resistor that is connected to ground through non-inverting terminal. So, if the resistance are equal, that is R is equal to R3 and RA is equal to R4, then the output voltages is given by and the voltage gain is +1. So, resistance will be equal, then we can again consider the gain will be equal. If these input resistance are unequal, the circuit becomes a differential amplifier. So, from the concept wise we already know the differential amplifier working. So, what it does? So, the differential amplifier exactly operates as a subtractor. So, no doubt it will going to the difference of two inputs only comes as an output. So, that can be easily made as a subtractor. So, producing a negative output when V1 is higher than V2. So, when we are going to deal with an inverting amplifier, we are going to have a input, that is when V1 is higher than V2, we will get a positive output, and a negative output will be get when V1 is higher than V2. When V1 is greater than V2, the output will be negative, and also when V1 is lower than V2, the output will be positive. These are the things we need to remember for a voltage subtractor. For V1 is greater than V2, negative output will be got. So, for V1 is lesser than V2, positive output will be got. So, next will be the voltage follower. Voltage follower in the sense in this configuration we need to remember about the feedback. It is having a different feedback, that is what that completely in the previous feedbacking we are partially fed the output to the input terminal, but here the completely it has to be turned into the input, which will going to give us a voltage follower circuit. Is a special case of a non-inverting amplifier. So, for an voltage follower application, we need to have a non-inverting configuration where all of the output voltage is fed back to the inverting input by a straight connection as shown in figure. So, here what we made, a straight connection is made from output to inverting terminal, and this will be in a non-inverting configuration. The straight feedback connection has a voltage gain will be of 1, and since the gain is 1, the voltage follower having a gain of 1. The most important feature of the voltage follower configuration are its very high input impedance and its very low output impedance. Because of its very high input impedance and very low output impedance, we are able to achieve the voltage follower application, and we are able to get voltage gain, we are able to achieve the gain of 1. These features make us easily to act this voltage follower as a nearly buffer amplifier and for interfacing high impedance sources and a low impedance loads. So, buffer circuits were usually used for high impedance inputs and low impedance loads, where we are going to use this buffer circuit. So, in that cases we are going to use this voltage follower circuits. For this, the impedance, there is a input impedance will be 1 plus open loop gain whole into Zin, that is internal impedance again, and the output impedance will be output impedance, that is internal output impedance divided by 1 plus open loop gain. This is similar to the closed loop gain of a non-inverting amplifier. Next we move on to integrator and differentiators. These are the two different circuits which are going to help us in dealing with the mathematical operations. Integrator is which is basically summing process that determines the total under area of the curve of a function. So, we need to find the total area under a curve of a function, means we need to integrate or integrate the values. So, for that purpose we need a integrated circuits. So, next another type is differentiator. This differentiator, which is a process of determining the rate of change of a function. Rate of change of a function has to be determined. In such cases we are going to use the differentiators. Very first we consider the op-amp integrators. The op-amp integrator circuit is as shown in the figure, where we are having the feedback is different here. This is the main thing we can observe from the figure, that is having a feedback which is having a feedback as a capacitor, not a resistor as in previous case, which is having a capacitor. So, this will going to act as an integrator with a feedback with a capacitor. The magnitude of the output signal is determined by the length of the input present. So, whatever the magnitude that we are going to measure in the output, that will be determined by the length of the input that is present, that will going to deal with the output. So, this is a major concept under the integrator circuit, and this will going to help us also study in the timing diagram also. Here if we consider, if the voltage is applied like this, initially there will be no current, because the capacitor is in open circuit, the feedback loop will be in the open circuit initially with a high impedance. So, when it going to charge, the impedance decreases and the capacitor starts discharging and makes the feedback loops short circuits, the current will be flowing. So, the output will be increasing. So, we can able to get the output in the output terminal. So, this is what we can able to achieve with the help of integrator. Next, move on to the integrator derivation. So, here from the picture we can able to find the capacitor and also the ramp is generated in the output. So, one of the major application of the differentiator is to getting a ramp signal. For getting a ramp signal also we will use a integrator circuit to get a ramp signal, because for high frequency value, high frequency voltages, the capacitor will discharges very fastly. So, this will be useful for producing a ramp output. So, the plates of capacitor is equal to the charge on the capacitor. So, that is divided by capacitor, that is Q divided by C. Then the voltage across the capacitor is output V out, that is therefore minus V out is equal to Q by C. This is what the basic thing that we can get from the circuit configuration. If the capacitor is charging and discharging, the rate of charge of the voltage across the capacitor, that is given by like this, V C is equal to Q charge on the capacitor divided by C, and this V C can also be written as V x minus V out. We can observe Vx why we written, because here is a inverting amplifier that we are inverting configuration is used for an integrator, that is why Vx comes. So, whenever Vx comes we need to remember the virtual ground concept. So, Vx is equal to 0 minus V out. Therefore, differentiating the above equation, we will get minus dV out where Vc is equal to Q by C. So, dQ by dt C divided by C into dQ by dt into C will be the expression for this. But here dQ by dt is an electric current. So, this since the node voltage here of the integrating op amp at its inverting terminal is 0, that is x is equal to 0 here. So, the input current IN flowing through the input resistance R in, that will be given by IN is equal to V in minus 0 into R in, that is equal to V in divided by R in will be the I in. So, current flowing through the feedback capacitor C, that is IF, will be given by IF is equal to C into d V out divided by dt. So, assuming the impedance is infinite and impedance is infinite, so no current flows into the op amp. The impedance is infinite, so there will be no current flow through the op amp. Therefore, nodal equations at the inverting input terminal will be like this: I in is equal to IF. We need to consider the input terminal. I in is equal to IF. I in we can substitute the value V in divided by value here, it is here V in divided by R in. IF also we know IF is equal to C into d V out divided by dt. So, by rearranging this we can get V in divided by V out into dt divided by R in C, that is equal to 1. So, now we are able to get the output for the op amp integrator. So, we need to integrate these things, we will get the V out is equal to minus 1 by R in into C, integration from 0 to t V in by dt. This will be equal to, after simplification, that will be equal to minus of j omega r c into V in. Therefore, the V out expression that we got minus j omega r c into V in will be the output voltage. So, this will be the output voltage for an integrator. Let us come to the end of the session. Let us have a brief summary. The summary deals with the first thing that we are going we discuss in the session is summing amplifier, which has 2 or more inputs, and it is having the output will be the summation of all the inputs that will going to appear in the output. The subtractor will be also called as differential amplifier. The subtractor will be having a difference of 2 inputs that we discussed in the subtractor amplifier. Next, we dealt with the voltage follower, which is going to have a gain of unity and having a direct feedback from the output to input. And also we dealt with the integrator, where we are going to use integrator for different mathematical applications to find the total area under a curve of a function. and we also derived the equations for it, the output voltage for an integrator. Some of the questions of the session are: define summing point, what is the value of RF divided by R for a 5 input averaging amplifier, what is the feedback element in an ideal op amp integrator, for a constant input voltage to an integrator, why is the voltage across the capacitor linear, what is the feedback element in an op amp differentiator, how is the output of a differentiator related to the input. References for this session are talkingelectronics.com and allaboutcircuits.com, and also the textbook for the subject are Operational Amplifiers and Linear Integrator Circuits by Robert F. Coughlin and Frederick F. Driscoll, Op Amps and Linear Integrator Circuits by R. A. Goikwad. This ends the session. Thank you.